Okay, so I want to talk about what's going on in these animations with hopefully a simple example. And I don't expect you guys to understand all of this. I just want to show you what's going on.
Okay.
Okay. So I can have an equation like this. Y equals x squared plus ax plus 1.
Okay.
All right. And this is, you know what shape this is going to be, right?
Yeah.
This is called what?
A parabola.
This is called a parabola. Do you know what a parabola looks like?
It's kind of like that.
Yeah, it's kind of like a U shape. And the shape is going to vary based on
what A is.
What A is, right? Sometimes it might look like this, sometimes maybe it's a parabola over here, who knows. But one thing that's interesting that people like to study about parabolas is what?
It's like what happens when A is really big and what happens when A is really small.
Yeah, that's one thing people can study, but there's a particular property, not about this specific class of parabolas, but about parabolas in general that people like to study. What are some things that you've learned about quadratic equations?
Well, like how they factor, and like when you graph them, some parabolas don't touch the axis.
What's it called when they touch the axis?
The roots.
The roots. So one thing people like studying about parabolas is?
The roots.
The roots. And as you change A, the roots change. Okay? The roots are where this equals 0. But people also don't just study equations like this over the real numbers, where the coefficients are 1s, and like A could be 0, 1, 2, 3, 4, maybe minus 2, minus 3, minus 4, minus 5.
Yeah.
They like to study them over the complex numbers, where this number can be x plus I times y. Do you know what I is?
It's the square root of -1.
Yeah, and this is just a new class of numbers, right? Or I shouldn't say new, a different class of numbers than the real numbers. What's different about these numbers?
Well, they're imaginary.
They're called the imaginary numbers. It's harder to think about what the graphs look like, actually, because the imaginary numbers have 2 components, so they're 2-dimensional. So the graphs are a little bit harder to understand, but the neat thing is they still have 2 roots. And you can study the roots. And those pictures you saw, instead of being x squared, were x to the 5th.
So that's why there were 5 dots.
Right, there were 5 dots. Those are the roots of this equation. And one of the equations was actually this exact equation. And they let A go in the complex plane around a circle. So A was just going around a circle. So this variable was changing around a circle. And the roots of the equation were changing as this changed. And they produced some pretty interesting graphs. What are some things you noticed about how the roots changed?
Well, it was weird because sometimes the dots were like rotating and sometimes they were like moving around in a bigger arc.
Yeah. So sometimes the dots were rotating and sometimes they were interacting in slightly different ways, based on so you were looking at several different equations. One of them was this equation with A changing around the circle. One of them was this equation, ax squared. One of them was ax cubed. Can you guess what another one might have been?
To the 4th.
X to the 4th. And so the dots all seem to have very different properties.
Yeah.
As that was going on. And mathematicians really like to study those sorts of properties. What's going on? Why is it different? Why is it the same? Why, in some cases, did it look like there were 3 dots in the middle and then 2 dots interacting? Other cases, it looked like there were 4 dots in the middle and that dot orbiting.
And sometimes the dot was like in the center.
Oh, sometimes there was a dot in the center?
Yeah.
Oh, wow. Cool. Cool. So, a neat thing that was discovered, I think in the 1800s, although I didn't do a lot of preparation for this because I just saw the form this thing last night. So you have y equals x squared plus ax plus 1. It's known how to solve this equation. How do you solve this equation? What's the idea?
You can use the quadratic formula.
Yeah, there's actually a formula that just gives you the two roots of this. For the next two equations up, x cubed plus ax plus 1, and sorry, not y squared, y equals x to the fourth plus ax plus 1. There are also formulas for solving these equations, and these were found by, I think, several Italian mathematicians, like maybe in the 1600s. The one who they're known for, I think, is Cardano, but he may have stolen the formula from someone else. But in the 1800s, it was proven that cubic equations and higher.
Are these like beyond the fifth equations?
Fifth degree equations or higher. It was proven by a very young mathematician named Galois that these have no general, there's no formula for this, or higher ones. You can't solve them in general. So when you're looking at those fifth degree roots bouncing around on the graphs, that's very mysterious behavior. And people are going to try to understand that behavior, but the interesting thing is you're not going to be able to understand it in a way that you can write down a formula for them, which is pretty remarkable, right?
Yeah, you have to solve them individually.
If you even can solve them individually. You might not be able to even write down what the solutions are, or write down them. Like, sometimes you can write down the solutions of these equations, like it might be square root of 5 plus 1 over 4 and square root of 5 minus 1 over 4, for example. Those might be the two solutions of an equation like this. So you can write them down. But for these, in general,
there's
no formula that tells you how to write them down. And he proved that, and he was very young when he proved that, around age 20. Pretty cool, huh? And you know what happened to him the next day after he wrote down the proof?
What happened?
He was killed in a duel.
Very exciting life.
Yes, a very exciting life. Very exciting life. So what I've done, and hopefully it's finished in the time we were talking here, is I wrote down some, on Mathematica, back upstairs, I changed the x to the fifth to x squared and x cubed, and hopefully we can look at those and see if they're different. We should see 2 dots bouncing around here and 3 dots bouncing around here.
Okay.
All right, let's go take a look.